Good morning, everyone. We're going to start back this morning in chapter 8. We'll be probably through a majority of chapter 8 today. We will probably finish chapter 8 Wednesday, look at some review. I was actually looking at our schedule. I think we'll actually be a little bit ahead of schedule, and we'll get into chapter 9 by Friday. But I think we'll have plenty of time to even review chapter 8 here during Wednesday's lecture, or maybe at the start of Friday's lecture as well. Let's talk about the polarity of bonds. We were talking about ionic bonds so far. So ionic bonds are metals, nonmetals. They're characterized by their lattice energy, the energy to separate the ions, and we find that lattice energy for ionic compounds is going to be higher, the highest, when we have really highly charged ions. So the greater the magnitude of charge, like 2 plus, 2 minus ions, stronger attraction than plus 1 minus 1. So like calcium oxide, a lot more attracted, takes more energy to separate than like NaCl, plus 1 minus 1 NaCl, relatively easy to separate in terms of ionic compounds. But then we were seeing for covalent bonds, we were sharing electrons. So we were beginning the sort of topic of sketching Lewis structures. We're going to take a break for a little bit from Lewis structures for a few slides to talk about bond polarity and start to look at some trends of things that we call electronegativity, so we can compare that our different nuclei in bonds will have a different pull for the electron pair of the shared electron pairs in bonds. And let's begin this discussion to go back to an ionic bond. So let's start the discussion with something like lithium fluoride. Just because we know lithium fluoride is ionic, or at least it's the sort of prototypical compound that we would think of lithium, will lose an electron to go to plus, gives the electron to fluorine to go to minus. Then we have that electrostatic force of attraction between the plus and the minus. Being relatively small in the case of these ions is good. So LAF has among the plus 1 minus 1s, it has the highest lattice energy because it's the 2 smallest ions. H plus doesn't form an ion in the same way like lithium does. And we were talking also last time, if you recall, that hydrogen's ionization energy is about 2.5 times that of the other alkali metals. So hydrogen doesn't act like a metal. It's not metallic at room temperature. It's not going to make H plus with F minus in terms of like a solid ionic compound in the same way that lithium fluoride does. In fact, we know that when we look at something like HF, that this is what we would call like a molecular compound. We know LAF from all the way back in chapter 2, we're calling LAF ionic. So we know that these are 2 different categories of compounds to begin with too. Let's also then compare to something like F2. So the fluorine molecule, where each fluorine would have 1 valence electron, well, those valence electrons can pair up, make a single bond. So we have that single bond between 2 fluorines. Now in this case here, we were talking a little bit about formal charge, the idea that if you cut the bonding pair in half and kind of think, well, what's the charge of each F? Well, this fluorine atom here is net neutral charged. This fluorine atom over here is net neutral charged. So neither one of the fluorines is adopting a charge. And it's really because if you imagine there being a tug of war on that electron pair, you have the same nucleus. You have the same, 9 plus and whatever the effective charges that makes it out to the outer valence electrons. You have the exact same nuclei pulling on the electron pair. So neither one of the fluorines can pull the electrons more closely towards itself. In the case of LAF, it just says, well, give me the electron pair and you don't get to share it at all. And it goes minus and lithium goes positive as a result. Well, HF will be somewhere in between this. HF, we look at this bonding pair of electrons, instead of it being equally shared, if it were, it'd be neutral charged. So if that bonding pair of electrons in HF were equally shared, then we would have neutral H, neutral F in terms of their charges, but the actual charges that develop on H and F end up having partial charges. What we mean by partial is not 0, not minus 1 for F, but somewhere in between. So we end up with what we call a partial negative charge and a partial positive charge instead of our actual. So these would be what we consider our actual charges. The 0 charges, those would be the formal charges. The formal charges assume that the bonding pair is equally shared, but then the actual charges take into account the behavior of the nuclei. That fluorine has a stronger pull for electrons than hydrogen does. That's why F is going minus in LAF, but then hydrogen has a small enough nucleus that can still kind of pull on the electron pair a little bit and keep it relatively close towards itself and doesn't totally give the electron pair up. And then we shade this with what we call a dipole arrow. So the dipole arrow, just an arrow, usually with a line through it here, that we just put a line through an arrow that's a dipole arrow, just meaning that the electron pair is going to be closer towards fluorine than towards hydrogen. And so on average, hydrogen doesn't get its 1 electron to balance out to a neutral charge, so therefore we end up having a partial charge. In a couple of slides, we'll actually be able to put numbers to this. And I want to put numbers to it just so we can see that we can actually calculate what we expect the partial charge to be, so that we can see like sort of a magnitude of charge. And then what we end up seeing is, if you think of this charge for fluorine here being -1 electron, +1 electron, that it's about 0.4. So we'll see that calculation work out so that the charge on fluorine and HF is about -0.4, hydrogen's about +0.4. But not quite even to -0.5, but you can see it's between 0 and 1 for the charges, and then plus on H, negative on F. And so what we have is, in the case of bond polarity is a measure of how equally or unequally the electrons are shared in a bond. A nonpolar covalent bond is one where the electron pairs are equally shared. So we get the equal share of nonpolar bonding in the case of bonds like fluorine, where we have two atoms that are the same bonded together. It's like oxygen, O2, N2, Cl2. Any case where we have a diatomic molecule with the same atom, we have to have the same nuclei pulling on the electron pairs. We end up with a perfectly nonpolar bond. So if we look at something like nitrogen, we looked at this Lewis structure last time, then there's no dipole moment here. There's no unequal charges on the two ends. We have perfectly neutral charged nitrogen atoms in this molecule. So here the actual and the real charges and the formal charges on nitrogen are all 0. But then the case of nonpolar covalent bonding is where one of the atoms attracts the electron pairs with a greater force. So you can think of the atoms forcing the electrons by their pull to be closer towards the nuclei. That is the one that we call the greater electronegativity. So this is the atom that has the highest electronegativity. So electronegativity, some textbooks bring it up in like the chapter 7 topics when they're talking about, because it looks like, and it kind of is, a periodic trend, but it's a periodic trend an atom has in a bond. So electronegativity in and of itself doesn't mean a whole lot. It's sort of a property that an atom has when it pairs up with other atoms. So it's like a comparison of the sort of pull that an atom has relative to other atoms. So the next slide, we'll take a look at our relative electronegativity scale. Or actually, the next slide just looks at the charge distribution of those three molecules. So here, F2, the idea is that you get the same charge on either side. So one of the F's is in a different charge than the other F. We have the same charge here. And then green charge would be on the relatively neutral side. Blue would be positive. Red would be negative in charge. And you can see HF is developing some positive charge on hydrogen, some negative charge on F. Then LAF, a lot more positive charge. So we're getting more positive charge in LAF. And that's just showing you that here you have the full plus, the full minus. Here you have a partial plus and a partial minus. And then here, in the case of F2, you just simply have 0 charges. And that's a delta sign here. So like the symbol I'm writing here is the Greek letter delta for plus for partial positive, and then partial negative for delta negative. So then this slide here takes a look at the relative electronegativity difference, and you can see that the metals have a low electronegativity. They have a weak pull for electrons in bonds, and then our right side elements have a high electronegativity. You don't see the noble gases because the noble gases aren't forming bonds, so they don't have a property of atoms within bonds, so we don't see the noble gases on this trend here. They tend not to form bonds. In some like peculiar cases, you can get xenon to make bonds, but we're not going to concern ourselves with some of the rare cases of the noble gases forming bonds. So our noble gases don't really have an electronegativity property. Fluorine, you can see here, has the greatest electronegativity. Fluorine has sort of one thing really good going for itself and then half of another thing. So the really good thing fluorine has is it's small. And the other good thing that is almost perfect for it is that it has a relatively high electronegative, relatively high effective nuclear charge. If you recall, effective nuclear charge actually increases top to bottom. So it turns out iodine, in the case of the transition metals that are actually common occurring, astatine below it, it's not a very common transition metal. But if you look at iodine, for the 4 main halogens that we encounter a lot in nature, it's actually iodine that has the greatest effective nuclear charge. So you might think in the case of electronegativity, is it going to be that effective charge that's highest for iodine? But iodine is too big. So it's hard for the big atom to have that pull for electron pairs in towards itself. So it's the relative high effective charge of fluorine, but then it's small size. So it's the fact that fluorine's really small. And if you also remember in the idea of lattice energy, if we're talking about charge transfer, smaller is better. So Even though fluorine doesn't have as high of an effective charge as iodine, the fact that the fact that fluorine's a lot smaller than iodine gives it this really high pull for electrons. We have a lot of comparisons you can make here, where if you pair bonds that otherwise would look neutral, if you're looking at a Lewis structure where the atoms are neutral in charge, you can then use electronegativities to say, okay, fluorine, if it's in a bond with, say, oxygen, there's a lot of Lewis structures we'll write in this chapter. This one, I think, is actually in the notes later today to write the Lewis structure for OF2, but we'll see how we come up with this Lewis structure later. But if you're looking at this Lewis structure and saying, okay, we're evaluating this Lewis structure for OF2, we have electrons on oxygen pairing up with fluorines, lone pairs. The formal charges are all neutral. If you think about fluorine, it should have 7 valence electrons for a neutral charge. That's exactly how many electrons fluorine has here. So this is a neutral formal charge. Oxygen's formal charge is 0. So once you then sort of see, okay, the formal charges are 0, that's assuming that's assuming non-polar covalent bonding, perfectly equally shared bonding. Well, which of the atoms has a stronger pull for the electron pair? It's fluorine, because it's more electronegative. So fluorine's going to take these two bonding pairs and shade them closer towards itself so that the true charges of fluorine become partial negative, and then oxygen charge becomes partially positive charged. And whatever the negative charge of F is, of course, it would be 2 times that negative charge. So this would be 2 times the partial negative charge on the two fluorines. So if it's minus 0.1 on each F, and it would be plus 0.2 on O to balance out the overall charge to be neutral. So oxygen, you can see here, goes positive, fluorine goes negative. Now this kind of goes all the way back to chapter 4 on assigning oxidation numbers. If you remember, oxidation numbers were pointing towards fluorine's always -1. So you might remember oxidation numbers would have had fluorine at -1. In this compound, oxygen would have been +2. And we mentioned how the oxidation number system didn't say that the true charges of O and F would be +2 and -1 in this compound, but just that we're predicting that fluorine will be the negatively charged atom and oxygen will be the positively charged atom. What the oxidation number rules were just really alluding to and we're getting at is that fluorine's more electronegative than O. So in a bond, fluorine's going to be the one that goes negative. It's going to pull those electrons more closely towards itself. If you compare O to F, fluorine, smaller, higher effective charge. That's what's leading those electron pairs to shading more towards the fluorine. You can see the electronegativity of hydrogen is not nearly as low as the other, as the alkali metals. And so hydrogen, therefore, is not considered to be an alkali metal. It's in the group, it's in the same part of the periodic table as the alkali metals, but in and of itself is not a metal. And you can see that the presumption would be that really high ionization energy of hydrogen is dictating that it doesn't have as low of an electronegativity. So that's why hydrogen is going to keep a hold of its electron more predominantly. Now, there's some textbooks, I think a lot of high school books, our old book used to do this. We don't really define this anymore because it's kind of tricky. If you look at a lot of metals versus nonmetals, you may come up with an electronegativity difference that's not super great. The greater the difference, the more ionic. The lesser the difference, the more covalent, the more nonpolar the bond is. If you take 2 fluorines, the difference is 0. So 2 fluorines, the difference is 0. So no electronegativity difference at all, no charge being developed in something like F2. But if you get to a relatively small difference like the CH bond, the CH bond has 2 atoms that aren't particularly electronegative. The difference isn't very big. So like a CH bond and something like methane, not a very electronegative bond in the case of CH bond. So this is a relatively like nonpolar bond. We have to also talk about molecular polarity. Molecular polarity comes up in chapter 9. Once we look at molecular shapes, we'll get a sense that there will be bonds that are polar in molecules. So molecules can have polar bonds, yet somehow end up being nonpolar molecules. We'll have to address that topic later. So when we look at bonds in this chapter, we're looking at a particular bond. Is it polar or is it nonpolar? The CH difference, that's one where I look at that and say, well, that's not a particularly polar bond. There's really not a lot of charge being developed on CNH and a molecule like methane. If we look at like water, H2O, there's a much bigger difference of electronegativity. Water is going to have really important charges that develop on the H and the O. And you can sort of start to see, well, hydrogen's less electronegative, O's more electronegative, O is going to be the negative atom. And that's also then why oxygen in water has the negative oxidation number, hydrogen has the positive oxidation number. You could even make sense of like calcium hydride. Remember these compounds here where hydrogen goes and has a negative charge? You can even see here, well, hydrogen has the greater electronegativity, so it's going to be the atom that wants to develop that negative charge. So it's not necessarily, like there's no real difference of electronegativity that allows me to classify a bond as ionic, polar versus nonpolar. I'm just kind of being generally like, if it's the exact same atom, it has to be nonpolar. So if it's like F2, Cl2, O2, it has to be a nonpolar bond. If the electronegativity difference is greater, we're shifting towards more polar character, more ionic character. So the greater the electronegativity difference, the more ionic the bond is, the greater the charges you would expect it to be developing on the atoms. But I wouldn't worry about saying, is the difference 2.0 to call something ionic versus covalent? I just look at it as a continuum, that the greater the difference, the more highly the charges, and then generally metal, non-metal. I still want us to think that those are generally still going to be classified as ionic regardless of the electronegativity difference. So if I know I have a metal paired up with even like bromine or chlorine, that's going to be the chloride or bromide ion. I don't want us concerning ourselves too much with the electronegativity difference, because if you take like bromine, compare it to, you know, like iron or something, it's such a small difference. You may be like, is that polar covalent or is that ionic? I would still call it ionic and not really worry about the difference. It's more about rank ordering bonds in order of increasing polarity. So increasing polarity would be by increasing difference of electronegativity. So like if we're comparing like BF, the bond in BF3, so the boron-fluorine bond versus say like carbon-fluorine bond, well, the CF bond not as polar, not as polarized, not as highly developed in charges as like the BF3 bond. So it's more like rank ordering the polarity trends of bonds by greater differences of electronegativity. So we'll see some examples of that, like a question like this here. So which bond below is the most polar, just thinking about relative differences of electronegativity. So if we're constructing, sometimes in these problems here, it's kind of best to just reconstruct a periodic table and just think we're increasing towards F in both directions. And so the like NF bond's going to have a greater difference of electronegativity. So like the NF bond should have a greater electronegativity than the OF bond. The F2 bond is the lowest because it's the same. This one here would have the perfectly non-polar covalent character. So the F2 bond here, this would be the only one on the chart that we'd expect to be perfectly non-polar because it has the same atom with the exact same electronegativity. Okay, so hopefully we're back in shape here. So non-polar for F2. Now, what about this difference here, like N and Cl? Well, NCl, we're going lower differences in electronegativity. The difference between N and Cl can't be as great as NF, just because we know chlorine has a lower electronegativity. So the greatest difference has to be NF for these choices. So the NF bond has to have the greatest electronegativity difference. The difference between NO and NCl might be tricky. If I had said to rank order all of these, you would probably need the exact number. So if I wanted to know, is it NO, then NCl, or the other way around, you would need that electronegativity chart. But if you look at the chart, N and Cl actually have the same electronegativity. I believe they're both 3.0 without flipping back, kind of watch. Okay, so for this question here, we weren't being asked to rank order that challenging, tricky question between NO versus NCl. If we were asking you that question, we would need to give you the electronegativity chart. But I would still expect, even though the difference between NCl and F2 are both 0 of electronegativity differences, I would still say F2 has to be perfectly 0. NCl, I think it would just be magic if it were exactly 0. So I would expect the NCl difference to be greater than the F2 difference. So to be perfectly nonpolar, same atom. Okay, so now this chart here is showing us a comparison between a few things. It's showing us HFs, HCl, HBr, HI. And it's also talking about a quantity, a mathematical quantity we can quantify called the dipole moment. We can actually measure this experimentally. So dipole moment mu is equal to the charge difference. It's the magnitude of charge that's being exchanged between the atoms. So the magnitude of that charge is what we call Q. So it's the charge that's being separated by the distance of the bond length of the molecule. And so R is the bond length. And there's like an interesting question here, which is, well, what happens for HF to HI? Because again, we have this issue, HF, like we know fluorine's small, we know it has the highest electronegativity, and we would probably predict it would have the highest overall magnitudes of charge. because its electronegativity difference would pull the electron pairs closer towards itself. So we would probably expect that the magnitudes of charge would be highest for HF, and then of these four, lowest for HI. So we'd expect that probably as you go from HF to HCl to HBr to HI, that the magnitude of charge, that Q, that partial negative, partial positive charge magnitudes would become smaller as we become presumably less polar. So we also can see the dipole moment becomes smaller as you go from top to bottom. So the dipole moment, that magnitude of charge, that Q times R, is becoming smaller towards HI. And so this here is making me want to say, okay, this is probably less polar. And then what would it mean to be less polar? Like one case you could say, well, it's smaller dipole moment, but I would say it's really the Q. The Q value, the partial charge it's developing, this is really where you look at the polarity. Like we would expect the magnitudes of charge to become smaller on the atoms of H and I and HI compared to the atoms on H and F and HF. Well, you can quantify it. Now the actual calculation will be on the next page and I'll present the data, but in the next slide too, but it's just comparing this bond length and then this dipole moment here that's been experimentally measured. We have to look at what the dipole moment D units mean in order to solve the problem. But then we can also see the electronegativity difference is dropping. So electronegativity difference are what sort of play a key role in the magnitudes of charge that develop on the atoms. So the bigger the electronegativity difference, we'd imagine bigger Q. So let's see if we can calculate Q and put some numbers to this problem. And then this is also going to be what I call like a proof of concept problem. Like that just means you probably won't be expected to do this problem again later. There's a few examples on some of the daily quizzes that I wouldn't focus on too much because I doubt we'd ask you to solve this math question on a test. But I think it's important to look at because it gives us a mathematical model for being able to see, well, what do we mean by partial charges? Can we put numbers to this sort of problem here? And so we're given the bond length and the dipole moment from the previous page here. An angstrom, if you forget, is equal to a 10 to the minus 10 meters. So 1 angstrom is equal to 10 to the minus 10 meters. So the bond length would be equal to 0.92 times 10 to the minus 10 meters. So we can do that math really easily and quantify that bond length and just that unit times 10 to the minus 10 meters. The unit of debye, named for physicist Peter debye, is shown here, that 1 debye is equal to 3.34 times 10 to the minus 30, and then coulombs times meters. Coulombs, the SI unit of charge, the SI unit of length is the meter. So the debye is just a non-SI unit for this quantity of dipole moment. And so then if we want to calculate the charge on fluorine, we also have to think, we have to quantify it in electron charge units. Like the charge of an electron is 1.6 times 10 to the minus 19 coulombs. So if we did this problem for LIF, presumably the charge on F should come out to be minus 1.6 times 10 to the minus 19 coulombs, because that's the charge of one electron. So when we're comparing this to something like lithium fluoride, that we're really thinking minus 1 electron's charge is 1.6 negative times 10 to the minus 19 coulombs. So the connection to like what an electron's charge is comes up in this problem. So if we're saying minus 1, I want to hopefully see that this is less than minus 1 electron. Okay, so we're just going to use this equation that the dipole moment mu is equal to that charge magnitude times r. We're trying to calculate Q here, so it'll just be mu, the dipole moment divided by r. We just have to account for units. And again, I'm going to go relatively quick because I'm not going to expect that you necessarily repeat this calculation, but it is still relatively straightforward. We're just taking the 1.82 unit of debye, doing the conversion into the SI units. And it's coulombs times meters. And then we divide that by the bond length r. In meters, we see why we want it to be in meters, so that it cancels into the coulomb meter units. The debye units cancel. And this gives me the unit of charge in coulombs. And let me go ahead and just work this out here in coulombs, and we'll convert it into electron charge units right after. Just 1.82. Now, if we're repeating this calculation, if I really wanted you to do it later, I think it's really just important to see a reminder. It's 10 to the minus 30. Like we see Planck's constant times 10 to the minus 34. So a lot of times we just blindly enter this as e to the minus 34, but it's e to the minus 30. So 1.82 It's 3.34 e minus 30, and then divide by 0.92 e to the minus 10. I get 6.61 times 10 to the minus 20. And that's less than the charge of one electron. So that's less than our electron charge. And if we want to quantify, well, how much of a partial electron is it? We'll just convert it into the charge of an electron. So just use the charge of one electron. 1.602 times 10 to the minus 19 coulombs. Well, that's the charge of one electron. And it's 0.41. I usually just use the unit E. And again, this would be like if I had -1, that'd be -1 electron. If it was +1, it'd be +1 electron. And so the charge is 0.41. So the charge on the H is plus 0.41. And the charge on the fluorine atom is negative 0.41. Because here we have the partial negative and the partial positive. I just think it's neat that you can put numbers to this. And you can see, well, what do we mean by partial charge? What we mean is it's not quite 0. It's not quite -1. It's not even to halfway. And this is one of the most nonpolar covalent bonds that there are. So most of your polar covalent bonds are going to be less magnitudes of charge than this. So if you look at like a CF bond or an OF bond, you probably wouldn't expect the magnitudes of charge to be nearly as high as these magnitudes here. If you were to do the problem for like HI, I think it works out to, it's either 0.04 or 0.07 electron charge units. So you can definitely see as you go down electronegativity differences, the Q plays a role. What you're changing is the charge magnitude. So if you make the electronegativity difference really high, you make the Qs really high, and then you make for a polar bond, a really polar bond as a result. If you make the electronegativity differences smaller, you make the Q magnitude smaller, not as polar covalent. So it's kind of getting a sense that the more polar the bond, the greater the magnitudes of charge. This then leads into a lot of things later that we'll develop. Like when we look at liquids in chapter 11, we'll see that when you have molecules that are polar and also have these really small charges, then they're going to be that more attracted. They're going to have a strong attraction for other molecules that have those small charges as well. So it leads into like hydrogen bonds. Who's ever heard of like hydrogen bonding intermolecular forces? I bet a lot of you guys have heard of hydrogen bonds. The hydrogen bond in like water, the reason why water has a strong attractive force with another water molecule is you have hydrogen with a positive, partial positive we now see, and then oxygen we see has a partial negative, and those two atoms are pretty small. So they have almost like that ionic force of attraction because you have charge that's being developed on really small centers. That gives you a strong attractive force. If you take those same charges but put them on bigger atoms, there's really not, there's not much attractive force between larger atoms that then have those same charges. It's really a consequence of having a small hydrogen with a high positive charge on a molecular compound that gives water a lot of its, very interesting and useful properties. Okay, so that's how we can calculate charge magnitudes. Again, I don't expect you to repeat the calculation, but I think it's useful for us to see what we mean by partial charges. Now, let's get back into sketching Lewis structures so that we can learn, okay, like how can we write a Lewis structure? We have a slightly different rule for diatomic molecules than we'll see for larger molecules. Assembling a structure using a dot diagram is sometimes easy, sometimes it's hard. Like our first starting point sometimes might be, can I get there with a dot structure of like O and C? And the issue here is I have a hard time kind of rearranging the electrons and kind of knowing, okay, I might end up with the structure with a dot structure that looks like this, but then I don't satisfy the octet rule. If I look at the C, it's deficient of an octet. O actually has an octet, it has all 8 electrons. When I'm thinking about the octet rule, is it satisfied? I'm thinking count all the electron pairs around an atom, so I have these for oxygen, so I'd have 8 around O, but I only have 6 around carbon in this structure. So then how do I come up with a Lewis structure using like the dot structure method of just start with the Lewis dot diagrams of C and O? Well, the answer is I really don't. come up with a useful structure that way. I kind of go back to the drawing board. So to go back to the drawing board to me would be to look at CO, count up how many valence electrons the Lewis structure should show. Like my Lewis structure should show carbon's 4 valence electrons. It should show oxygen's 6 valence electrons. So I count up my valence electrons for the 2 atoms because they're the outermost electrons. If we have more electrons shown than this, then it would have to be an ion. Like if I somehow sketched CO, if I said, well, why don't I just take CO like we did here and say, well, okay, we'll give it an octet because an octet appears to be important. Why don't we just do that? What's the problem with that Lewis structure for CO? This Lewis structure here is wrong because it has too many electrons. That might be a good Lewis structure for CO2-. Like if we count the electrons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 electrons. To have 12 valence electrons in CO would mean it had to pick up a charge of 2-. So this might be, and this probably would be, the perfect Lewis structure for a molecule CO with the 2- charge. Well, it turns out that's not an ion I've ever even heard of. It's not one that we're probably ever going to see an example of. So this is not the Lewis structure for neutral CO. So we start thinking of a Lewis structure. It has to have the right electrons shown for the charge of the molecule. Otherwise, it's a Lewis structure for some other molecule. In this case, this Lewis structure would be the Lewis structure for like CO with the 2- charge, not neutral CO. So neutral CO should only have 10 electrons shown. Well, we saw a molecule with 10 valence electrons. That was N2. So N2 also has 10 valence electrons. That's its valence electron count, nitrogen 5 each. And so we ended up with the structure for N2 that looked like this. Well, it turns out CO has that same Lewis structure. That CO has the same triple bond and then lone pair on the C, a lone pair on the O, just like N2 did. So it's like if our rule for diatomics is we're just going to satisfy the octet rule whenever we can, the only way we can do that for CO is with a triple bond. And I'm going to have a hard time getting to that triple bond if I was like starting with the Lewis dot structure over here. Do you see, how do I know when to move an electron from O onto C and make that triple bond? I don't know. I just kind of go back to the drawing board though and think, okay, 10 electrons has to be a triple bond. If I had 12 total electrons, then it would be double bond. If it were 14 total, like F2Cl2 have 14 valence electrons, it goes single. Now, what about the formal charge of carbon? Like we haven't really seen, I don't think we've seen a molecule yet that had non-zero formal charges. The formal charges, picture what the charge of this thing would be. Remember I said dot structures don't write 3 on a face? I'm just writing 3 on a face because of the triple bond. So I'm just kind of picturing, break this bond in half, and then I end up with something that looks like this. What would the charge of that be? Carbon with 5 valence electrons, what's the charge of that atom? It's -1. It's picked up an extra electron. So this is a -1 charged carbon. If I had oxygen look like this, again, we wouldn't draw a dot structure this way. This is again just from breaking the bond in half and kind of thinking, okay, what would this charge be here? Well, oxygen should have 6 electrons. If oxygen had 6 electrons, it would be neutral charge. So this has to be positive. So the way I usually think of sketching determining formal charge is I first write, well, what's the valence count for the atom? Carbon's is 4. The valence count of oxygen is 6. That's how many valence electrons those atoms should have to have a perfectly neutral charge. And then I just break the bond in half. So formal charge just says break the bond in half, calculate the charge. So it's 4 minus 5 for carbon, that's -1. And then oxygen would be 6 minus 5 for +1. This is a really weird Lewis structure. This is a Lewis structure where we have more negative charge being developed on the lesser electronegative atom. Doesn't that seem wrong? In a way it is wrong, but it's actually not wrong in terms of Lewis structure. This is still the best Lewis structure of CO. There's actually a lot of properties of CO that are really important. Like we talked before, how carbon monoxide, deadly poisonous gas. It looks a lot like CO2. It's formed by incomplete combustion. When we run out of O2 for a hydrocarbon to burn, makes CO, can kill you. And it actually kills you in a way because the carbon attaches to your hemoglobin. So instead of O2 attaching to your hemoglobin, which is what you breathe, carbon attaches. So it attaches through the carbon, not through the oxygen, because the more negative charge is what attacks the hemoglobin. So the negatively charged carbon attacks hemoglobin, turns out to irreversibly bind to hemoglobin. So it binds to the hemoglobin, doesn't come off. Oxygen falls off. and then myoglobin carries the CO2 back. I mean, I forget all of biology, but this is basic biology, is that the O2 reversibly binds, falls off, goes to where it's needed in the body, and then myoglobin forms and carries the CO2, which then removes when you breathe. So CO2 and O2 go on to hemoglobin, myoglobin reversibly. CO goes on irreversibly, and it stays attached. And your only chance of survival is getting to fresh air and making new hemoglobin. Could be blood transfusion if you're in the hospital, if you get there in time. But the interesting property of CO, though, is that it's the carbon that carries that negative charge. Now, the bond is still polar, meaning the electron pairs in the triple bond are going to shade towards the oxygen, and the true charge on oxygen isn't quite +1 in the real charge. You can think this is kind of like a real versus actual charge. There is a problem on one of the daily quizzes. If you're interested in it, it's interesting to see that you can put a dipole moment and a bond link to this problem, and the true charge on oxygen is only actually about 0.02 units of charge positive, but it's still positive, and then carbon is negative, about negative 0.02, but still negative, meaning that the triple bonds can be still closer to the more electronegative O, but we still carry these true charges. Carbon's still negative, oxygen's still positive in the real molecule. So a triple bond for CO2, really interesting molecule. A lot of things you can say about CO that are important. I think since it's such an important molecule, a lot of you guys are doctors, or future doctors, I hope, that you should know about this important molecule. Okay, but now let's just look at Lewis structures of NO+, NO-. Very similar, but then they also get into the topic of, well, what do we do when we have ions? Like, how do we quantify how many electrons should be shown in the Lewis structure when we have a plus versus a negative charge? Well, it's the same basic starting point. I take 5 valence electrons. That's the ordinary valence count for nitrogen. I'm just looking periodic table, 5 valence electrons. The entire row of N has 5. The entire row of O has 6. The entire row of the halogens has 7. So I'm taking 5 plus 6 for the N plus O. And then to get to a positive charge, I have to subtract an electron. That's how we get net positive, is by removing electrons. So I have to remove one of my valence electrons and only show 10 total. If I, at the same time, kind of think of NO-, very similar, 5 plus 6 valence electrons, and then, but +1 for that extra negative charge. To get to a net negative charge, I have to add a negative particle. So I have to add an electron. So cations, we're removing electrons from the valence count to get to net positive. Just like that's how we get to net positive for like sodium. We take an electron away, minus an electron, get to plus. To get to a plus, we have to remove an electron. To get to like F-, we're adding an electron to fluorine. So to get to a negative NO, we have to add an electron. Okay, so then we get to 12. So NO+ is really the exact same Lewis structure as above because it has 10 electrons. So it ends up being that exact same Lewis structure, triple bond. This is also a really interesting Lewis structure because if you quantify the formal charges, they're also kind of peculiar. They seem to kind of be not what you might have expected, but I have break the bonding pair electrons in half, 5 minus 5. That's a neutral formal charge nitrogen. And oxygen, despite being more electronegative, oxygen wants electrons more than nitrogen, and oxygen ends up going +1. Should have 6, only has 5. So it's the same environment as CO, so it's +1 formal charge. Now, this molecule here is also smarter than our Lewis structures are just a model, okay? So a Lewis structure doesn't compel the molecule to do what we just wrote. The molecule can then say, well, my O atom has a greater pull for electrons because O is still smaller, still has a higher charge. The nucleus has a higher charge and a pull for the electrons than the nitrogen's nucleus. So think when I'm talking charge here, I'm talking about the nuclear pull, not the formal charges. The pull of the nucleus of oxygen is greater, so it's going to want to pull those bonding electrons closer towards it. So the real charge is not going to be as high as +1, and then as a result, we're going to develop actually positive charge, so we're going to increase that partial positive charge on nitrogen. So thinking about how a Lewis structure kind of tells us what would the charges be right before we consider what the bonding pair electrons are going to do. Like that's the perfect environment for a Lewis structure to show us what do we think the sharing of electrons looks like, and then allow the relative pull to kick in, and then think about how that pull is going to change some of the charges from those formal charges that we're writing. NO-, 12 electrons, well that's perfect for a double bond. So I don't have to go to a dot diagram to get to the structure. I just know 12 electrons is just like O2. So it has a double bond. And then the resulting formal charge here is that nitrogen, I break the bonding pair in half, nitrogen has 6 valence electrons now. And so nitrogen's formal charge should be 5, has 6, so it's -1. And oxygen should have 6, and it has 6, so it's net neutral. So we have a 0 formal charge for oxygen, and in this molecule, a -1 formal charge for nitrogen. Now, would you expect those to be the real charges in the real molecule? Probably not, because oxygen's still more electronegative. It's going to pull the electrons closer towards itself. So oxygen, we would expect, would be partial negative. So we expect oxygen would have some partial negative charges, and then the negative charge wouldn't be as high as -1 as a result. So we'd have probably still some partial negative on nitrogen as a result of electronegativity differences kick in. I don't want us to overly dwell on even predicting partial positive versus negative charges, but I think they're really helpful to think about. It's really helpful to think the Lewis structure shows us charge magnitudes where nitrogen, why would nitrogen be more negative than O, given that nitrogen has a less electronegativity, less of a pull for electrons? Well, it's just because that's what the Lewis structure was compelled to do. Then the nuclei can kick in terms of their relative pull for the electrons and kind of shift the electron charge distribution around the molecule. One thing that maybe isn't obvious, I should point out, the sum of the formal charges has to be the charge of the molecule, like +1, -1 for CO. So if you sum up all the formal charges in a molecule, you have to get back to neutral if it's a neutral molecule. So +1, -1 for CO. We had 0 and +1 for NO, that's net positive, and then -1, 0, net negative for NO. So if you sum up all the formal charges, just like if you sum up all the oxidation numbers, you should get to the charge on the molecule. Same thing with the formal charges. If you sum up the formal charges, you should get back to the charge on the molecule or ion. And then if you sum up the true charges, you should also calculate and quantify the true charge on that molecule or ion. Now, the real tricky part of this chapter, I don't think it's tricky actually, but the meat and potatoes of this chapter is writing Lewis structures for then most other molecules that have 3 or more atoms that aren't simple. Like water, I think is simple. Like we did the Lewis structure for things like water, NH3, CH4. There are some molecules where you can very easily come up with a dot structure and come up with the bonding nature for something like water just through the dot diagram. That's fine, but what about something like SF4? What about something like ClO3 with a negative charge? What about some of these ions that we've learned how to name, like nitrate, carbonate? We can figure out their Lewis structures too, but a lot of those are going to be trickier than starting with a dot structure. They're going to need a set of rules that are like the ones here, and then even a molecule like water, CCl4, that we previously looked at, or CH4, NH3, we can apply these rules and get to the exact same Lewis structure. But these rules are, we got to sum up the valence electron count. We have to identify the central atom. The central atom is usually the thing first, like PO4 3-, phosphor is the central atom. So CCl4, carbon's the central atom. So the central atom is usually pretty easy to identify. The book mentions the central atom is often the lesser electronegative atom, but it's usually the atom we write first. So when we're writing like SF4, well, sulfur is the central atom because we wrote it first. So usually we're writing that atom that's central first. Like H2O, occasionally we write the hydrogen first. So there's some molecules where maybe we'll write the central atom last. And then oxygen actually turns out to be not the lesser electronegative too. So there's other examples where finding the central atom is usually not the tricky part. Hydrogen can never be a central atom, right? Because hydrogen can only form one bond. Hydrogen can't bridge 2 different things together. So hydrogen's always on the periphery of the molecule anyways. So it's usually not too hard to identify the central atom. We then attach atoms to the central atom, and we start with single bonds because that's the least bond that you can have. You complete the octets of the non-central atoms with non-bonding electrons. And if we have any electrons that are not yet assigned, the only room that's left is on the central atom. And so then we have this rule here that I think we're going to have to, as we go, come back to a little bit. But it's about when we consider making multiple bonds. It's going to be thinking a lot about partial charges. It's going to be thinking about reducing magnitudes of charge through multiple bonds and not expanding multiple charges to make double bonds. So we'll see this rule play out in some examples as we continue, and we'll revisit this rule here because it's pretty complicated. But if we're just starting from really basic Lewis structures, it's like for CCl4, Well, let's count up the valence count. And I hope this becomes, or is really easy, because I'm just thinking carbon on the periodic table is just in the group 4. So it's just 4 valence electrons. And then chlorines in the halogen group, there's 7 each. So 7 times 4, that's 32 valence electrons that have to be distributed and shown within the Lewis structure. And then we were told to find the central atom, which is carbon, single bond the non-central atoms to the central atom. Give those atoms an octet. Now chlorine needs 8 electrons to fill its octet. If it's hydrogen, hydrogen doesn't need these electrons. So for chlorine, we need to fill the chlorines with an octet. And then that's 8 electrons per chlorine, and times 4, that's all 32 electrons. So if we saw that we had electrons unassigned, then we'd be putting them onto the central atom, but we don't have any electrons left over to be placed onto the central atom within this Lewis structure. The only last consideration would be, do we, for some reason, need to make double bonds somewhere? Well, the only reason we would ever make double bonds is to minimize formal charges. Well, if I calculate my formal charge, do you see that carbon is 0? Is that really easy to see? That's to say charge neutral, formal carbon, formal charge of 0, 4 minus 4. Should have 4 electrons closest to it, and it does. I'm just breaking each of the bonds in half. Chlorine should have 7, they have 7, they're all 0. So all neutral charged atoms around the molecule of CCl4. And so we're done. That's the best Lewis structure for CCl4. Now the molecular shape is next chapter. So the molecule isn't necessarily going to be flat, so don't think we're interpreting 3-dimensional shapes yet. We'll see those develop into chapter 9. But so no need to consider multiple bonds in a molecule like CCl4. Now what about BF3? BF3, boron only has 3 valence electrons. It's right next to carbon. And then 3 times 7 for the fluorines. That's 24 total electrons. And so central boron, 3 fluorines. Give the fluorines their octet with lone pairs. Now notice it didn't say to give the central atom an octet with electrons, just the non-central atoms. So the non-central atoms we fill with electron pairs. I don't do that to the central atom. I have to compare my electron count. So I go 8 electrons around each of the fluorines. That's 24 total electrons distributed. In the Lewis structure, I have none left over. If I wrote 2 electrons on boron, do you see the problem would be, that would be like BF3 with a 2- charge, not BF3 with a neutral charge. So boron here has a net charge of 3 minus 3. It has 3 electrons closest towards itself, so it's net neutral, and so are the fluorines. So the fluorines are net neutral. The boron's net neutral in terms of its formal charge. That turns out to be pretty good, because if you think about charge, like if I'm a nucleus, and if I'm going to have a really high positive or really high negative charge, I don't really have the nuclear charge to make charges of that variety. So 2 extra electron pairs on boron here, 1 is a different ion, but 2, boron's charge isn't very high. The effective charge of boron at size is relatively big. It doesn't have the pull for electrons to be able to pull those electron pairs to make a charge of boron with those extra electrons. So we probably wouldn't expect boron to be able to pull electron pairs in towards itself. Well, what about the possibility of taking an electron pair from fluorine and making a double bond? So let's make a double bond here, so we lose the electron pair. That's like what these structures are showing here. Is, do we make those double bonded structures? Well, if we think about those double bonded structures, what they're doing to boron is they're changing it to, should have 3 electrons, but now it has 4 electrons closest towards itself. Do you see if we break the double bond in half, we have 1, 2, 3, 4 electrons closest to boron, making it -1 formal charged. And then fluorine should have 7, now it only has 1, 2, 3, 4, 5, 6. So the fluorine with the double bond is now +1. Why would fluorine give electron pairs up to an atom that doesn't even want the electrons in the first place? So if you're thinking about boron, boron would have to physically, through its nucleus, through its effective nuclear charge, pull the negative electrons in to make a double bond. It doesn't have the power to do that. In fact, fluorine's doing the opposite. Fluorine's saying, I actually want the electron pairs more than the boron. So let me come back to this structure here, and wrong button, erase button. So let's erase this and say, well, let's not do that at all. Let's put the electron pairs back, because the fluorines are really trying to pull electrons away from boron. So fluorine's not trying to give, like fluorine could care less about boron's octet. Boron's octet is meaningless to the fluorine atom. What fluorine wants to do is what fluorine wants to do, which is pull electron pairs towards itself. And it just can't totally make F minus here because boron has a little bit of a pull. Boron's trying, but it can't really keep a hold of the electron. It just doesn't give the electron up permanently, so it still has a pull, and it still ends up bearing a positive charge as a result. So that makes boron here partial positive as the fluorines really develop that partial negative charge. So the real molecule is going to look something like this. This is what the real molecule looks like, polarized bonds. It looks nothing like those structures. I don't even like the book saying those are less important. These are not important. So the book says those are less important resonance structures for BF3. They're not important at all. Like those don't help us understand the bonding in BF3 at all because boron's octet is meaningless. So boron exists deficient of an octet, and that's A-okay. There's nothing wrong with BF3 existing with a structure less than an octet. SF4, let's do this one relatively quick and then we'll finish here for today. But 6 plus 4 times 7, sulfurs and oxygens group, we end up with 34 total electrons. The thing that's nice with this structure here is we finally get to use the case of what do we do when we have electrons left over. So I fill the fluorines with their octets. Only 32 electrons, 8 per fluorine. That leaves behind 2 electrons. Well, where do I put them? Where do they go? They got to go somewhere. Fluorine's already full, though. We put them on sulfur. And you might be thinking, well, sulfur was full, too. Sulfur had an octet as well. Why do we put them on sulfur? Well, one, the rule says to. The rule says when there's extra electrons, just put them on the central atom, and don't worry about expanding the octet. Fluorines are doing the hard work for us. They're actually moving electron pairs off of the sulfur due to the electronegativity difference to help make room for those extra electrons. SF4 is a real molecule. It exists. It's relatively stable, and it has a lone pair on that sulfur. Okay, so we will end here for let's end with the quiz. Keyword for today is zinc. And yeah, so that'll do us for today, and I'll see you guys back here on Wednesday.